Hey, welcome back to Fan Mama Physics. This is the last video in this whole series, even in circular motion. Unless I make more later in the future years. But, yes, I've been sitting around making all these videos, so a little bit tired. So hopefully, I'll have enough energy to get us through this last example, example 4 in 6.2, part 2, which we apply Newton's universal law of gravitation to circular orbits. This one, we're going to talk about geosynchronous orbits. First of all, we need to know what geosynchronous means. And if you don't already know, basically what that is when a geosynchronous orbit means that if you have a satellite that is orbiting the Earth, if it's just orbiting the Earth at some random period, it might be out of sync with the orbit of the Earth. What that means is, if I have a globe, if I have a circle somewhere, no, too bad, I don't. I'll use a mouse instead, okay? Imagine this, a mouse is the Earth, okay? And keep in mind, the Earth is also rotating around its axis, which is going to give us night and day relative to where the sun is shining. So because our Earth is rotating, if I have a satellite moving around the Earth, if I want the satellite to be directly on top of the location that I'm interested in pinpointing, then this satellite is going to have exactly the same period of rotation as my Earth rotating around its axis. So if it takes 24 hours for my Earth to rotate back to its original position, is facing towards the sun, then that's going to be exactly the same period of my satellite. My satellite's also going to have a period of 24 hours before it comes back to where it started, so that it's always directly on top of whatever it's surveying. So once you see that a satellite, when it says something has a geosynchronous orbit for Earth, then you know the period has to be exactly 24 hours. And what is 24 hours in seconds? We take 24 times 3. First of all, every hour we're going to get 3,600 seconds. So we're going to times that. And that's going to give us 864,00 seconds. Okay, so now that we know the orbital period of this satellite, let's do example 4. Find the orbital radius of a satellite that is geosynchronous above the Earth's equator. Okay, so the reason why I asked for equator is just to make it simple. Otherwise, the orbit might be a little bit funny, because the satellite would be directly above where it is at an angle, so the geosynchronous orbit might be a little bit funny. So the equator is probably the easiest way to go about this scenario. So to say that's the equator and the satellite is, say, over here, okay? And it's also going to have the same period of the Earth's axis rotation. So here period is going to be 86400 seconds, which is exactly 24 hours. We're roughly, because it's in real life it's slightly off, but anyways. Okay, so the question is, we want to find the orbital radius and we want to find the speed of the satellite. So there are two things we have to do. So the first things first, let's find the orbital radius. Ha 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 ha. This question is sneaky because you might notice that it is much easier to find the speed of the satellite and then use that to find the period. So I think the intention of this problem was to get you to write that complicated equation that I showed us in the last video that basically used the fully written out version of the F-net equation. So that combined the period, the radius instead of the speed, so that you use this to find the orbital orbital radius, then use that to find the orbital speed. So, if you're just solving this problem, you might just find the speed first, then find the orbital radius. That is okay, but it's still important to understand how to arrive at that equation, which, guess what? You know what? I'll just do it again so that you have it in your toolbox. we know that for sure that the satellite is going to experience an gravitational attractive force towards the center of the Earth, in which that's going to provide your centripetal acceleration. So we write our FNet equation, which Fg is going to be equal to ma, in which the centripetal acceleration, I'm going to use the full-blown value with orbital period and orbital radius. So that's going to be 4 pi squared r over period squared. Fg is Newton's universal law of gravitation, big G, big M, small m over r squared, and this is going to be small m, directly copying what I have on top. And a few things are going to cancel. First of all, this mass is going to be able to cancel, okay? And, this r is going to be able to move to the bottom over there. So, but let's take a look. We want to find the orbital radius. So let's solve that by multiplying the radius up to the top, okay? So we're going to get big G, big M equal to 4 pi r, and then this r is to the power of 3 because of exponent laws. We add up the exponents, divided by t squared. We want to move everything that is not r to the other side because we want to solve for orbital radius. So we're going to move t squared to the top, okay, so that's going to be multiplied to the top. Everything else we're going to divide. So divided by 4 pi squared, divided by 4 pi squared over here, that's going to get rid of this. And ultimately, we're going to be left with orbital radius to the power of 3 equals to big G, big M, t squared over 4 pi squared. Okay, solving for r. We need to take not the square root, but we need to take the cube root. So it's going to look like this. Taking the cube root gets rid of the power of 3, to the exponent of 3. And to solve for the radius, we have this cube root of big G, mass of the Earth, times the period squared over 4 pi r. Okay, and putting all the numbers inside, we're going to get 6.67 times 10 to the power negative 11. And mass of the Earth, 5.97 times 10 to the power 24. And the period, remember it's 24 hours, is going to be, I'm running out of space, but 864 000 in brackets 4 pi squared. Okay, well then, let's put it all in. Phew. Now, it's a little messy, so double check what you put into your calculator, because I know some of you are going to mess up. I will mess that up too sometimes. So, divide by this, and, oh yeah, if you put in your calculator, a good way to take something to the power of, to take the cube root, it is also, you can also take it to the power of 1 over 3. You take a power to the 1 over 3 as a fraction is the same thing as taking the cube root. Okay, so this is going to give me 422.269110. Okay, and that's going to round up to how many sig figs? 24 hours. So probably is so that's probably going to be 3 sig figs. So 4.22 times 10 to the power of let's see, that's about 7 meters. Phew. Okay, so now we have the orbital radius. We can then find the orbital speed using this one, 2 pi r over period. Okay, so then we use this one a lot. This is 2 pi. We found the orbital radius is 4.22 times 10 to the power of 7. and then divided by period, which is 864000, which is the 24 hours. Okay. Okay, so then we put this one into the calculator. We get 307. 307. Oh, I see. I had an extra 0 here. That's why. Okay. Yes, so that's going to give you 0.070 meters per second. Perfect. Okay. So that should be about 3 sig figs, not 2 sig figs. Okay, well then. So this is your geosynchronous example. And if you did it the other way, calculate speed and go back to calculate the orbital radius, that could work. I just wanted to do it the other way around so that you can see how to manipulate a more, say, complex case here, okay? Alright, hopefully you learned something. Thank you for watching. Van Mama Physics signing up.